Okay, good morning, everyone. Okay, we are considering this section 4 in section 4, which considers the L'Hopital's rule, which is, as I said, very important. And I will ask some questions definitely in the exam from this section. So please listen carefully today. Okay, first, in order to use the L'Hopital's rule, okay, there are two cases, and there will be some variants which apply the L'Hopital's rule. So we will first consider some cases. So as I said, if you have an expression of form f of x over gx type, okay? So if you have some, say, f of x over gx type function, and as x approaches a, and this a can be any value, any number, even on infinity. Okay? So as x approaches a certain number a, if both numerator and denominator go to zero, then the limit of f of x over gx will be computed from limit of f prime over g prime. Please do not apply the quotient rule. You need to differentiate the numerator and denominator separately. Okay, so f prime, the derivative of the numerator over the g prime, the derivative of the denominator. You estimate these two derivatives, and then you let x go to a. As x approaches a, if f prime over g prime converges to a certain value, that's the limit of the original problem. And I considered one example here, and I also considered this sine theta over theta as theta goes to zero. So this is one example. Another example we may consider can be found from the exercise. Say, limit of sine x minus cosine x over tangent x minus 1, and you let x approach the quarter pi. Now, at quarter pi, sine x and cosine x have the same value, the square root of 2. Please note that sine quarter pi and cosine quarter pi are both the square root of 2 over 2. Right? So as x approaches the quarter pi, the numerator will approach 0. And in case of the tangent quarter pi is 1. So the denominator also approaches 0 as x is very close to the quarter pi. So we can apply the L'Hopital's rule. So if I differentiate the numerator, what do I get? If I differentiate sine, you get cosine. And if I differentiate cosine, you get minus sine. So since I already have minus in front of cosine, we get plus sine x. That is the derivative of the numerator. And what is the derivative of the denominator? If I differentiate tangent, you get secant x squared. if I differentiate -1, you get 0. And then if you let x approach the quarter pi, then, as I said, cosine at quarter pi is square root of 2 over 2. And sine is also square root of 2 over 2. And secant is the reciprocal of the cosine. So secant will be square root of 2. And then I need to square that value. So if I simplify the numerator, you get square root of 2 over square root of 2 squared. So square root of 2 over 2. So that is the limit of this expression, and by the L'Hopital's rule, that will be the limit of the original problem. One more example. Actually, if I consider, say, okay, the e to the 2t minus 1 over sine t, and then if we let t go to 0, then as t goes to 0, this exponential function e to the 2t will approach the value 1. So as t goes to 0, e to the 2t minus 1, the numerator approaches 0. And in the denominator, sine 0 is also 0. So as t goes to 0, both the numerator and denominator approach 0. So I can apply the L'Hopital's rule. So if I differentiate the numerator, what do I get? When I differentiate the exponential function, you get 2 times e to the 2t by the chain rule. Excuse me. When I differentiate -1, you get 0. So that would be the derivative of the numerator. If I differentiate the sine t, you get cosine. And then if you let t go to 0, the numerator, the exponential function, approach 2 times e to the 0, and cosine t approaches the value 1, and e to the 0 is 1, so the limited value will be 2. Just one note. One note. What if I slightly modify the function? And if I have e to the 2t minus 1 over cosine t, and then if I let t go to 0. Now, in this case, the numerator approach the value 0, but on the other hand, denominator does not approach 0 as t goes to 0, right? So in that case, you cannot apply the L'Hopital's rule. So for this problem, we cannot apply the L'Hopital's rule because limit of cosine t as t goes to 0 is not 0, while the limit of e to the 2t minus 1 as t goes to 0 is 0. So 1 goes to 0 while the other converges to some non-zero value. So in that case, cosine t is approaching the value 1. So the limit is 0 over 1, which is 0. So if, as I said, if both numerator and denominator converge to 0 as your t converges to a certain number, then we can apply the L'Hopital's rule. Otherwise, we cannot. So that is the first type of the L'Hopital's rule. Here is another example. Yeah. As x approaches the value 1, the numerator x to the x squared minus x, which can be factored as x times x minus 1. So due to this x minus 1 term, numerator will approach the value 0. And as x approaches 1, denominator also goes to 0. So we can apply the L'Hopital's rule. Then that means we can consider the derivative of the numerator over the derivative of the denominator. And then you can consider the same limit. So if I consider the derivative of the numerator, when I differentiate x squared, you get 2x, right? So that will be 2x. And then if I differentiate x, you get minus 1. If I differentiate x squared, you get 2x. Okay. And if I differentiate negative 1, you get 0. So if you let x go to 1, then limit will be 2 times 1 minus 1 over 2. So 1/2 will be the result, the limit of this problem. So that is the approach obtained using the L'Hopital's rule. If you do not want to apply the L'Hopital's rule, what you can do is, since the numerator and denominator, when factored out, they both have x minus 1 in common. So I can cancel this x minus 1. Then what remains will be x in the numerator and x plus 1 in the denominator. And then if you let x go to 1, the numerator approaches the value 1, while denominator approaches the value 2. So if you just consider the ordinary calculation with this factoring and cancellation stuff, you can find this limit. But the approach obtained from the L'Hopital's rule seems to be much simpler. So if you have some problem, the limit of certain expression, and if this expression is defined by f of x over gx, and as x approaches a certain number, if both numerator and denominator go to 0, then we can apply the L'Hopital's rule. So please remember this. And let me skip this. Now, the second type of the L'Hopital's rule is this following. If when you have similar shape of a function is given, now as x approaches a, if both numerator diverges to infinity or negative infinity, and denominator gx diverges to infinity or negative infinity. The sign doesn't matter. One may diverge to plus infinity while the other diverges to negative infinity, or both diverge to negative infinity, or both diverge to plus infinity. It doesn't matter. The sign doesn't matter. Okay, so if numerator and denominator diverge to plus or minus infinity, okay, as x approaches a, then we can apply the L'Hopital's rule. That is the second type. So in this example, if I have these two polynomials, Okay, or if I have this rational function, x squared minus 1 over 2x squared plus 1, and then here x diverges to infinity. Okay, so that means the value of x increases without bound. Then numerator diverges to plus infinity, denominator also diverges to plus infinity, so I can apply the L'Hopital's rule, which means I can differentiate the numerator and denominator and consider the same limit. So when I differentiate numerator, you get, so this is the case without using the L'Hopital's rule. So as I said, I can apply the L'Hopital's rule directly. So what I mean is, if I differentiate numerator, what do I get? 2x. If I differentiate denominator, what do I get? 4x. And then when I consider this a limit, well, before I consider this limit, since x is common here, I can cancel this x. So that is the limit of 1/2 as x approaches infinity. So the limit will be 1/2. So that is the result of this limit. Okay. So L'Hopital's rule is the following. As I said, if you have the problem of limit f of x over gx type problem, and if both f and g go to 0 as x approaches a, or if both diverge to plus or minus infinity, in that case, the limit of f over g can be computed by limit of f prime over g prime. So this is the L'Hopital's rule. Okay, is it if numerator goes to 0 while denominator diverges to plus or minus infinity, you cannot apply the L'Hopital's rule. Okay, you can apply the L'Hopital's rule when both converge to 0 or both diverge to plus or minus infinity. So please remember this. Please be careful. And as I said, as x approaches a, this a may be just an ordinary number, or a may be plus or minus infinity, or even when we consider one-sided limit, say as x approaches a from the right or from the left, or as x approaches plus or minus infinity, if as long as the conditions I just mentioned, that if that condition holds, you can apply the L'Hopital's rule. So here, when I consider this problem, as x approaches 1, log x approaches 0. X minus 1 approach 0. So both the numerator and denominator converge to 0. So I can apply the L'Hopital's rule. So if I differentiate the numerator, I get 1 over x. If I differentiate denominator, I have just 1. And then if you consider the limit as x approach 1, then as x approaches 1, the numerator approaches the value 1, while denominator is just 1 always. So the limit will be 1. If you do not apply the L'Hopital's rule, then you need to rely on some properties of E and some other stuff. But if I use the L'Hopital's rule, the calculation will be simple. Okay. Before we consider the next section, let me consider some examples in the textbook. So, for example, if I consider a limit of square root of x over 1 plus e to the x, and then if you let x diverge to infinity, in that case, both the numerator and denominator diverge to plus infinity. So I can apply the L'Hopital's rule. If I differentiate the numerator, you get 1 over 2 square root of x. And if I differentiate denominator, you get e to the x. So if I simplify this term, we have 1 over 2 square root of x times e to the x. Now, as x approaches infinity, if as x diverges to infinity, numerator is a number 1, constant. And denominator is a product of the number 2, square root of x, and the exponential function e to the x. Now, the square root of x diverges to plus infinity, and e to the x also diverges to plus infinity as x approaches infinity. So the numerator just increases without bound. Denominator is a constant 1, so the limit will be 0. Another problem, if I consider a limit of x plus x squared over 1 minus 2x squared as x approaches infinity, as x diverges to infinity, the numerator x increases, x squared also increases, and their sum increases without bound. So the numerator just increases to infinity. And in case of the denominator, 2x squared increases without bound, but since I have negative in front, so the denominator just decreases to negative infinity. But as I said, the sign doesn't matter. As long as this numerator and denominator both diverge to plus or minus infinity, you can apply the L'Hopital's rule. That means you can differentiate numerator and denominator separately. So if I differentiate the numerator, what do I get? When I differentiate x, you get 1. If I differentiate x squared, you get 2x. And when I differentiate denominator, when I differentiate 1, you get 0. When I differentiate negative 2x squared, you get negative 4x. And if you let x go to infinity, now at this point, the newly obtained denominator 1 plus 2x still diverge to infinity. And denominator negative 4x also decrease to negative infinity. Anyway, both numerator and denominator diverge to plus or minus infinity. So we can consider the L'Hopital's rule one more time. So in the previous example, we considered the L'Hopital's rule. If I use H for the L'Hopital's rule, then this L'Hopital's rule was used once. But in the case of the second example, we use the L'Hopital's rule here, and then I need to use the L'Hopital's rule one more time. Then when I differentiate 1 plus 2x, you get 2. when I differentiate denominator, you get negative 4. So when I consider this a limit, this is a constant number, so the limit will be this constant, or in other words, minus 1/2. That will be the limit of the original problem. Okay. So these are some examples of the L'Hopital's rule. Please remember, when both the numerator and denominator go to 0, or when both diverge to plus or minus infinity, we can apply the L'Hopital's rule. Okay. So please remember, now, if you have a product, so of two functions, f of x times gx, and then you want to consider the limit of that product as x approaches a. Now, if one of these two functions, f or g, if one of the two functions converges to 0 while the other diverges to plus or minus infinity. Okay, so one function converges to 0 while the other diverges to plus infinity or minus infinity. In that case, you need to change, I mean, you need to change the expression. So you need to convert f of x times gx to f of x over 1 over gx. That is the same as f of x times gx. Okay, so one function stays in the numerator and the other one goes to the denominator using the reciprocal. So you replace this f of x times gx to this expression, then apply the L'Hopital's rule. We can apply the L'Hopital's rule because if, for example, if f is a function that converges to 0, then that means gx will diverge to plus or minus infinity. But since I have the reciprocal 1 over gx, this 1 over gx in the denominator will converge to 0. So I have 0 over 0 type, which means I can apply the L'Hopital's rule. If f is a function that diverges to plus infinity or minus infinity, then this 1 over this gx is a function that converges to 0. Then 1 over gx will diverge to plus or minus infinity. So I can still apply the L'Hopital's rule. Okay, so if you have this product f of x times gx, and if one function converges to 0 while the other diverges to plus infinity, then you need two steps. The first step is to convert this product into this form. In other words, one of these two functions goes to the denominator. And second step is to apply the L'Hopital's rule. Okay, so you need to rewrite this f times g using f over 1 over g or g over 1 over t, 1 over f. And then you can apply the L'Hopital's rule. So as an example, x times log x, and I have, yes, as x approaches 0 from the left, from the right. Okay, so as you know, the graph of the natural log function is like this. And as x approaches 0 from the right, the value of the logarithmic function diverges to negative infinity. So one function diverges to negative infinity. But what happens with to this x? As x approaches 0, the value of x decreases to 0. So x approaches the value 0 while log x diverges to negative infinity. Then, as I said, you need to convert one of these two, okay? You need to move one of these two functions into the denominator. So, for example, if I move x to the denominator, you get limit ln x over 1 over x. Please note that if you take ln x over x, then that is different from x times log x, right? I need to, when I move this x to the denominator, x must be converted to its reciprocal, 1 over x. And then you put that reciprocal in the denominator. And then you let x go to 0 from the right. Okay, and you can always use the L'Hopital's rule at this point because in this expression both log x and 1 over x diverge. So we can apply the L'Hopital's rule. That means I need to differentiate numerator and denominator. When I differentiate numerator, what do I get? The derivative of log x will be 1 over x. What is the derivative of the x 1 over x? 1 over x is the same as x to the negative 1. So if I differentiate it, you get negative 1 times x to the negative 2. And then you let x go to 0 from the right. So x to the negative 2, what is that? So we have 1 over x in the numerator and negative 1 times 1 over x squared. Let me multiply x squared to the numerator and denominator to simplify the expression. Then we get x in the numerator and denominator is just negative 1. And then you let x go to 0 from the right. As x approaches 0, the numerator x goes to 0, while denominator is fixed to negative 1. So the limited value will be 0. So that is the limit of this expression, or that is the limit of this expression, which is the limit of x times log x. So the limit will be 0. Okay. Now, if you want to move this log x to the denominator using its reciprocal, it is a little bit, it is more complicated to differentiate. I mean, the denominator is a little bit complicated to differentiate it. So that's why I moved x instead of log x to the denominator. But either is fine, either must be fine. Before we consider the next one, let us consider some example. What is the limit of, say, yes, the limit of square root of x times e to the negative x over 2 as x approaches infinity. Now, as x approaches infinity, square root of x will diverge. As you know, the graph of the square root function is this one, just 1/2 of the parabola. And the function is increasing function. without any bound. So square root of x will diverge to infinity. However, in case of e to the negative x over 2, the exponent diverges to negative infinity. Then the exponential function decreases to 0. So I can apply the L'Hopital's rule. So if I move one of these two functions into the denominator, so I will keep this square root of x in the numerator, and if I put this e to the negative x over 2 into the denominator, you get e to the x over 2. And then you will let x go to infinity. As I said, you can always apply the L'Hopital's rule. So if I differentiate square root of x, what do I get? You get 1 over 2 square root of x. If I differentiate e to the x over 2, you get 1 half of e to the x over 2. And you let x go to infinity. Okay. So what do I get? After the cancellation of 2, we get limit 1 over square root of x times e to the x over 2 as x approaches infinity. And as I said, as x approaches infinity, square root of x diverges to infinity. This exponential function also diverges to infinity. So the denominator increases without bound while the numerator is just 1. So the limit will be 0. So that is another example. Let us consider one more example. Yeah, how about this? Limit x to the 3 half times sine 1 over x as x approaches infinity. Okay, then since I have this sine x, sine 1 over x, due to this sine 1 over x, due to this, I want to express this by sine 1 over x, which is x to the negative 1 over x to the negative 1, which is 1 over x. Please note that 1 over x in the denominator is the same as x. I had x to the 3 half. If I use x in this denominator, then what remains will be x to the 1 half power. Okay, so I want to consider this a limit. Then as x diverges to plus infinity, and I have sine 1 over x over 1 over x. So for simplicity, let me introduce t to imply 1 over x. Then as x approaches infinity, t approaches 0. So t approaches 0 from the right because this t is also a positive number. And if t is the reciprocal of x, then x is 1 over t or t to the negative 1. So x to the 1 half will be t to the negative 1 to the 1/2 power, and I have sine t over t. Limit of these two products. Now at this point, as t goes to 0, what is the limit of this? As t goes to 0, t to the -1 diverges to infinity, right? So, and even when I have 1/2 power, the first term approaches infinity. Okay, then does the second term approach the value 0? Let's see. What is the limit of this? As t goes to 0, what is the limit of sine t over t? It is not 0, but 1. No, please note that the limit of sine t over t as t goes to 0 will be 1, not 0. So one term diverges to infinity, while the other term is approaching a finite and positive number. So this one converges to a positive finite number. Okay? And the other term, t to the -1/2, that term will diverge to infinity. So this product will be approaching infinity. Even though this is a product of two functions, you need to be careful. Even when you have a product of two functions, one function diverges to the infinity, while the other one is approaching a constant value, not 0, to a positive finite value. So, excuse me, the limit is just infinity. One more example. Okay, and then let me go to the next slide. So here I have, okay, the limit of log x of times tangent pi x over 2. Okay. And I want to consider the limit, say, as x approaches 1 from the right. And if you remember the logarithmic function graph, as your x approaches the value 1 from the right, log x converges to 0. Okay, then what happens with this tangent? As x approaches 1 from the right, pi x over 2. So given this is the graph of the tangent function, and as your x approaches this pi half from the right, so you are approaching this point from the right, then the corresponding tangent, this one, diverge to negative infinity. So the second term diverges to negative infinity. Now I have a product of two functions, and one converges to 0 while the other one diverges to negative infinity. So you can apply the L'Hopital's rule. So what is the remedy of this? How can I fix the problem? You can put one of these two functions in the denominator using its reciprocal. So usually people do not move log x into the denominator, but you put the other term go to the denominator. So if I consider the reciprocal of tangent, that is cotangent. So this is the same as log x over cotangent of pi x over 2. And then you let x go to 1 from the right. Now, I can apply the L'Hopital's rule, right? So if I differentiate log x, you get 1 over x. What is the derivative of the cotangent function? You get negative cosecant function squared multiplied by the derivative of pi half x. So that will give you pi half. Now, what is the limit of this as x approaches 1 from the right? The numerator 1 over x approaches the value 1. And I have, okay, what is the cosecant, the limit of cosecant pi x over 2? You need to remember the cosecant is the reciprocal of sine, and sine pi half will be 1. So this term, the cosecant square of pi x half, will converge to the value 1. So negative 1 times pi half. So the limit will be minus 2 over pi. So that is the limit of this product as x approaches 1 from the right. Okay, so one more time. In order to apply the L'Hopital's rule, your function is of form f of x over gx. And we can apply the L'Hopital's rule only in one of two cases. Number one, both numerator and denominator go to 0. Number two, numerator and denominator diverge to plus or minus infinity. Sign doesn't matter. And one application is this. When you have a limit of the product of two functions, if one converges to 0, the other diverges to plus or minus infinity, then one of these two functions will be moved to the denominator. And then you can apply the L'Hopital's rule. Now, another variant is this. If you have limit of f of x minus gx, and if both f of x and gx diverge to infinity, okay, so either both f and g diverge to infinity, or both f of x and gx diverge to negative infinity. In that case, there is no fixed method to convert this. Okay? In that case, you need to change the expression somehow. Okay? So there's no simple way for this type of a problem. So in that case, so if you have limit of f of x minus gx, and if your f and g both diverge to infinity at the same time, or both diverge to negative infinity at the same time, then you need to do something, okay, to convert this f minus g to this type or this type. I mean, you need to do something, okay, so that you have certain function over another function. So you need to convert some function over another function, and these two functions in the numerator and denominator must be 0 over 0 type or infinity over infinity type. That means both converge to 0 or both diverge to plus or minus infinity. So you need to do something to convert this into this. Okay? You need to do something. But this is something depends on f of x and gx. So this type of problem is a little bit complicated. So here is one example. Suppose that I have 1 over log x minus 1 of x minus 1 as x approaches 1 from the right. So as x approaches 1 from the right, as we observed before, log x is approaching the value 0. X minus 1 also converges to 0. So their reciprocals are divergent. Okay. So as x approaches the value 1, 1 over log x diverges to infinity, and 1 over x minus 1 also diverges to infinity. So infinity minus infinity type problem is given, and I need to do something. Okay, and in this problem, since I have f of x minus the gx, and f of x is the reciprocal of certain function, gx is another the reciprocal of another function. So what you can do is you can merge these two functions with a common denominator. So if I do that, so if I merge these two expressions with a common denominator, and common denominator will be the product of log x and x minus 1. So if I do that, if I merge them, this is the expression. Now, as x approaches 1 from the right, x minus 1 is approaching 0. Log x approaches 0. So the numerator is approaching 0. And as I said, x minus 1 is approaching 0. Log x is approaching 0. So their product will approach 0. So if I if I merge these two expressions, then both the numerator and denominator are approaching 0 as x approaches 1 from the right. So I can apply the L'Hopital's rule. That means I need to differentiate numerator and denominator separately. So if I differentiate x minus 1, you get 1. If I differentiate log x, you get 1 over x. And in the denominator, I have a product of two functions. So I need to differentiate these two functions one by one. When I first differentiate x minus 1, the derivative is 1. So 1 times log x is obtained. And then if I keep x minus 1 and then differentiate log x, you get 1 of x. If I multiply them, we get this. Now, okay, so in this case, since I have one of, yeah. So if I multiply x to the numerator and denominator for simplicity, you get limit of x minus 1 in the numerator and x times log x plus x minus 1. And then you let x approach 1 from the right. Now, as x approaches 1, x minus 1 in the numerator converges to 0. X times log x will converge to 0. X minus 1 converges to 0. So that means the numerator and denominator are approaching 0 as x approaches the value 1. So it's the situation I can apply the L'Hopital's rule one more time. So here I apply the L'Hopital's rule, and then if I apply the L'Hopital's rule one more time, when I differentiate x minus 1, you get 1. And in the denominator, when I differentiate x times log x, that is a product of two functions, so I need to differentiate one by one. So in x times ln x, if I differentiate x, you get 1 and you have ln x. And if I keep x and differentiate ln x, you get 1 over x. So x times 1 over x. And then if I differentiate x minus 1, you get 1. And then you will let x go to 1 from the right. Now, in this case, the numerator is always a constant number 1. What is the limit of log x as x approaches 1? 0. So the limit of this will be 1. Limit of log x is 0. And actually, the second term, x times 1 over x is always 1. The third value is also 1. So the limit will be 1/2. So that will be the limit of the given problem. And I obtained this by applying the L'Hopital's rule 2 times. But I need to convert the given expression into f of x over gx type function. And additionally, f of x and gx both converge to 0 or both diverge to plus or minus infinity. Okay? So in this specific problem, in this example 7, I just merged these two expressions with common denominator. Okay? But sometimes you need to consider different approach. So I considered this, we already considered this, and I have, yeah, something like this. If I have limit of cosecant x minus cotangent x as x approaches 0. Now, as you know, cosecant is the reciprocal of sine. So sine the let me consider this the right and this 0 from the right for simplicity. Then the cosecant, which is the 1 over sine, will diverge to infinity. So this function diverges to infinity. And please note, remember that this cotangent function is cosine over sine. And that also diverges to infinity because the cosine function converges to 0. cosine converges to the value 1, while sine function that converges to 0. So this one is also divergent. So I have infinity minus infinity type problem. Then for this function, there is nothing to merge. But if I rewrite these two functions in terms of sine and cosine, they have sine as a common denominator. So at that point, I can combine these two. You get 1 minus cosine x over sine x. And as x approaches 0 from the right, the sine function decreases to 0. And 1 minus cosine x also goes to 0. So we have a 0 over 0 type expression. So I can apply the L'Hopital's rule, which considers the limit, but the numerator is differentiated. So 1 is differentiated to 0, and negative cosine is differentiated to sine x. And the denominator, sine x, is differentiated, you get cosine x. And if you consider this limit, as x approaches 0, sine function converges to 0, while cosine converges to 1. So the limit is 0. Okay. So that's how we consider infinity minus infinity type problem. Okay. Some okay. Now, one more application we want to consider is the following. This one is a little bit confusing though. So you need to definitely write down some types where you can, okay, excuse me. So before I consider this section, previously we considered the L'Hopital's rule, okay, that considers f of x over gx type function is considered. And in order to use the L'Hopital's rule, one of two conditions must be satisfied. Either both f and g converge to 0. In other words, 0 over 0 type. Or both f and g diverge to plus or minus infinity. In other words, infinity over infinity type. So that's the L'Hopital's rule we considered. And then we considered some special cases where we can apply the L'Hopital's rule. One application was limit of f of x times gx. And if one of these two functions is approaching 0 while the other one diverges to plus or minus infinity, what did I tell you? You need to convert the expression somehow to f of x over gx type. And then, I'm sorry, if you have this, then one of these two, f or g, will go to the denominator using its reciprocal. Second variant was f of x minus gx type. If both f and g go to infinity, or if both f and g go to negative infinity, then you need to do something. Okay? When I say both f and g go to infinity and both f and g go to the negative infinity, I forgot to tell you one example. If I have, say, e to the x, okay, and um, uh, e to the x minus e to the negative 2 um, something like ln x as x approaches 0 from the right, then ln x goes to the negative infinity, and if I have 1 over x, then 1 over x 1 over x diverges to plus infinity as x approaches 0 from the right. Okay, so 1 over x diverges to plus infinity, and ln x diverges to negative x, negative infinity. But I have this negative sign in front of log x, and negative of negative will become plus. So due to this negative sign, negative log x diverges to plus infinity. So one function diverges to plus infinity, the other one also. So we have infinity plus infinity. So the limit will be infinity. Okay. There is no room to apply the L'Hopital's rule in this case, because 1 over x plus negative ln x, if I rewrite the expression like this, then that is the sum of two functions, and both the functions diverge to plus infinity, not infinity minus infinity type. Okay, both are increasing. Okay, so we cannot apply the L'Hopital's rule for such problem. Previously, if f and g both diverge to infinity and both diverge to negative infinity, then this difference is a little bit complicated one, so you need to modify somehow. But if one diverges to infinity while the other one diverges to negative infinity when f of x minus gx type is given, that's a different story. Okay, so please be careful. And now the third variant we want to consider is the following. Suppose that you have f of x to the gx type function. This is, please note that, as I said, this is not a power function. Okay, and this is not an exponential function. So if you have f of x to the gx type function, and if one of these three conditions are satisfied, okay, then so what are these three? The base f of x converges to 0 while the exponent converges to 0. If the base the diverges to infinity but gx converges to 0, or if base f converges to 1 while gx diverges to plus or minus infinity. If you have one of these three situations, then you need to take the log function. Okay, so given you let this product, this function by y, and then you take the log function to this y to move this gx to the front of log f of x. Okay. Then you always have 0 or then probably one of these two functions will converge to 0 while the other one will diverge. Okay. Let me give some example. Suppose that I have this expression. Okay. As x approaches 0, sine function converges to 0. So the expression in the base will approach the value 1. But in case of the cotangent, which is cosine over sine, that diverges to infinity. So this is the third type. So in that case, you always take the logarithmic function. So you first define y by that expression. You take the log function. Then this cotangent function can be moved to the front of the logarithmic function. Then if I use the identity that is cotangent x is the reciprocal of the tangent function, we get this. And then 1 plus a sine function is approaching the value 1, as I said. So its log will converge to 0. And as x approaches 0, tangent function also converges to 0. Or in other words, in my previous notation of the cotangent function diverges to infinity while log function converges to 0. So you have infinity times 0 type. So anyway, if I rewrite cotangent as 1 over tangent, then I write down the expression as f of x over gx type, and both function converge to 0. So now I can apply the L'Hopital's rule. So if I apply the L'Hopital's rule here, I need to differentiate numerator and denominator. And then if I simplify, if I plug in 0 to x, then you get the value 4. And at this point, many students make a mistake. Please note that this 4 is the limit of log y. This is the limit of ln y. And what is the problem? We are looking for limit of y, not limit of log y. So this is my y function, okay? And y is e to the ln y. So this is y and this is e to the ln y, and ln y converges to 4. Okay? So this exponent converges to 4. So the limit is e to the 4, not 4. So many students make a mistake because they stop here. They got something, some numeric value, and then they just stop there without thinking the meaning of this value. Please remember, you took the logarithmic function, and this 4 is the limit of ln y. Okay? And our task is to find the limit of y, not limit of log y. So this additional step is needed to get this limit of the problem. Okay? Anyway, please review this section carefully and please try to solve some problems in the exercise. I will show some more examples next time, okay? But please try yourself as well, okay? Anyway, Thank you for listening and see you next time.